This chapter is about the decision tree method. Decision tree was proposed by Ross Quinen back in 1986, and this is one of the primitive machine learning algorithm. Uh, not many people are using decision tree these days. Many people use deep learning, etc. But we cover decision tree for a couple of reasons. Uh, First, this decision tree is actually the beginning of machine learning era. So this is important decision tree. And even though this algorithm is a little old and obsolete, some theories in the method is quite important, like entropy information theory. And lastly, this method has evolved into a random forest, which is quite competitive. And the contents of this lecture will be the following. We study how to construct the decision tree in a top-down manner. So decision tree is tree, so it begins with root node and it grows downward. So when you create a decision tree, we're gonna choose a certain attribute, and that attribute becomes a node of decision tree. And also we use entropy, information gain, and gain ratio as the criteria to choose the splitting attribute in decision trees. So we're gonna learn those. And finally, after the decision tree is constructed, we're gonna actually cut some branches and subtrees of decision tree in order to make the tree small and compact, simple. So we're gonna learn how to prune this decision tree after the tree is constructed. So this picture shows the example of decision tree. Uh, so in decision tree, each node, internal node, is an attribute, actually, attribute of data. And each branch here means the attribute value of the attribute. So in this case, this weather attribute has three branches, means three attribute values. And down here, this leaf node, these are class values, class labels. So it works like this. So you first compare the weather value, and if the weather value is rain, you come here and actually the answer is bus. You take bus. And if weather is sun, then you come down here and next step is to check the value of time attribute. So if the time is less than 30 minutes, then your answer is bus. You take bus. So something like that. So this is decision tree. So every internal node, in this case in blue, node in blue, means attribute of data. And each branch here means the attribute value. And the leaf node here down here, these are the class values of data. So when you have new class, you want to classify new data, then you simply follow the matching path to a leaf node. So as I said, when you have new data and you want to classify new data using this decision tree, then you first check the value of weather. So let's say the weather value is cloud, you come here, and then next you check the value of hungry. So if the hungry value is yes, you come here and the answer is walk. So you take a walk instead of bus. That's how it works. So we're gonna begin with an example here. So actually this example is from the original paper of the Ross Quinlan, which introduced the decision tree for the first time back in 1986. So we're going to use this example data and generate decision tree out of this data. So this data has actually five attributes, and the last attribute play is called class attribute or target attribute. So this is kind of answer, and these four outlook, temperature, humidity, windy, these are four input attribute. So using these four input data, you're gonna predict the value of target attribute play. Okay, that's how it works in this particular data. So we're gonna use this data and try to generate decision tree out of this data. Output of a decision tree algorithm. So if you run decision tree algorithm using the example data in previous slide, then the decision tree algorithm is going to generate something like this. So this is decision tree. So the data in previous slide is input, and this picture here in this decision tree is output of decision tree algorithm. So the part of the goal of this lecture is to learn how to generate a decision tree like this from input, like in a previous slide. That's the goal of this lecture. So okay, we're gonna build a decision tree out of data. Actually, when you build a decision tree, actually it consists of two phases. The first phase is data decision tree construction part. It's a top-down tree constructions. So in phase one, you actually build complete decision tree, and in phase two, it's called the bottom-up tree pruning. So in phase two, what you do is actually you cut some branches, you remove some subtrees. So that's what you do to actually make the tree small, simple, and compact. That's the second step, phase two. So we're gonna cover both of these phase. So in phase one, it's called top-down tree construction. So this is a decision tree. Decision tree is tree. So when you build a decision tree, and you start with root node or root attribute. Each node is attribute. So you start with the root attribute, and then uh, in each branch of attribute, you keep adding another new attribute. Okay, so you keep doing this all the way to the bottom until there is no other attribute available. Okay, so that's the phase one. So you start with the root attribute and keep adding new attribute to the branch of the node all the way to the end. So that's phase one. And phase two, what you do is so your tree is now constructed, but in phase two, you make the tree simple, compact. That's what you do in phase two. So actually what you do is you simply remove some subtrees or branches of the tree you created in phase one. Okay, that's what you do in phase 2. So we're gonna learn the detail of each phase later on. So as I said, decision tree is a tree structure. Okay, so that means it has root node, root attribute in this case. So you start with the root attribute. So that means you have to choose one attribute which goes to the root node. Okay, so we have many attributes in the data, and you choose one of them, and which becomes the root node of decision tree. Then the next question is that then how do you choose one attribute to be a root node? So for example, in the previous example, a play tennis example, there are 4 attributes we can choose from: outlook, humidity, temperature, windy, right? Actually, the play tennis is target attribute. Okay, so that's not the node of decision tree. That's our goal. Okay, that's something we're gonna predict. So we, in example data case, play tennis case, we have 4 attributes. So we choose one of them. Okay, and that becomes the root node of decision tree. So next question is, which one do you choose? What is the criteria of choosing one attribute over the other? Okay, that's the question. So the criteria is called a goodness function. Okay, so goodness function. So we have to decide what kind of goodness function you're gonna use to choose one particular attribute, right? So as a goodness function, we have many options. The first one is entropy, and also information gain ratio, and Gini. So these are possible candidate of goodness functions. So we're gonna study all of these as we go. Let's say we have data, sample data like this. We have attribute A, B, C, D, and for simplicity, let's say every data is binary, 0, 1. And we have a class, target attribute, class label as Y, N, okay? And in attribute A, okay, if you look at carefully, in attribute A, if attribute A value is 0, okay, A is 0, then every class value is Y, okay? Class A equals 0 means class value is Y. If attribute A is 1, then every class value is no, right? So this is very simple. If attribute A is 0, every class value is Y. And every attribute A is 1, class value is no. So this is our goal, right? We're going to predict this one. So in attribute C case, if attribute C is 0, we have 0, 0, 0, 0, okay? If attribute C is 0, this is Y, Y, N, N, okay? We have 2Y and 2 no. And if C is 1, okay, then we have 2Y and 2N, right? So if in an attribute C, if the value is 0, you have 2Y and 2N, okay? And attribute C is 1, class value is again 2Y and 2N, okay? So again, our goal is what? Our goal is to predict the class value correctly. So in attribute A case, if you know the value of A, 0 or 1, whatever, if you know the value of attribute A, it actually determines the class value. If attribute A is 0, that automatically determines class value Y as Y, right? If the attribute A is 1, that automatically means class value is N, right? So if you know the value of attribute A, we don't need to know the rest. We don't care about all the other attributes. Our problem is solved. You know the attribute A, well, it determines the class value automatically. Okay, we don't care about attribute B, C, D, whatever. Okay, so in terms of predicting class value, class attribute A is just the king. Okay, this is all we need. We don't need anything else. On the other hand, in attribute C, okay, again, the goal is to predict class value. In attribute C, and when attribute C is 0, we have 2y and 2n, okay? This is very unclear, okay? We cannot tell whether the value is y or n, okay? With 2y, 2n. When attribute C is 1, again, same story. You have 2y and 2n. So again, we cannot tell whether the class value is y or n, okay? We need additional information. So if you know the value of attribute C, whether 0 or 1, actually it doesn't help in terms of classifying, in terms of predicting class value. Okay, so in terms of classifying class value, attribute C is kind of useless. Okay, but in attribute A, if you know the attribute A, well, the problem is solved. Okay, it automatically determines class value. So if you compare attribute A with C, well, definitely when you build a decision tree, we prefer attribute A to attribute C. Okay, it's clear. So in attribute A, you choose an attribute value, attribute A value, whatever. The class value is homogeneous. In attribute A, when the class value is attribute A value is 1, every class value is n. Attribute A is 0, every class value is y. So what we need is actually when your attribute value is selected, then the class values are homogeneous or pure. That's the best scenario. Okay, so in that sense, we like attribute A. Let's look at the class distribution of attribute values from the previous example. I mean the play tennis example data. So the data has 4 attributes: outlook, humidity, windy, and temperature. So outlook has 3 values, that it has 3 branches, and for each value, these are the class values, okay, distribution of class values. So for example, in outlook is sunny, uh, there are 2 yes and 3 no's. In outlook is overcast, everything is yes. This is very good actually. And outlook is rainy, we have 3 yes and 2 no, etc. Okay, so as I said in previous slide, we like something like this, right? We want something like this, and we would like in this case the class values are homogeneous, same, pure. We like something like this. Okay, this is good, and this is also good because majority of values are yes. We have only one no, and the rest, many of them are yes. Okay, but here in this case, we have 3 yes and 3 no, and we don't like this. Okay, this is like the attribute C in previous slide, right? So you don't like this. So what the attribute we are looking for is something, the attribute value which has something like this. Okay, so we are looking for attribute whose value has something like this, something like this. Okay, Not something like this, not something like this, okay? So let's say we have attribute and its attribute value has many of these or many of these. That's good. We like that attribute. And if the attribute has many of something like this or something like this, well, we hate the attribute, okay? That's the basic rule of selecting attribute. So the more homogeneous the class distribution is, the better the attribute is. So which attribute are we gonna choose? So the rule of thumb is we choose attribute that produces the purest node. So what I mean by that is if we look at this example here, so for the attribute A, if A is 0, every class value is Y. And if A is 1, every class value is no, right? So class distribution for this attribute is very pure, right? So that's what I mean by pure node, okay? So we are looking for attribute with pure class distributions. So this case is kind of extreme, okay? So in reality, if we are looking for attribute whose attribute value generate class distributions as close as this. Okay, that's what the attribute we are looking for. Okay, and the next question is, so I said we are looking for attribute with pure class distributions. Then what do you mean by pure? How do we measure the degree of purity or certainty or clearness? Okay, that's the next question. We need a formula or number which measures the degree of purity, right? Or in opposite term, you can measure the degree of impurity or uncertainty or noisiness. So either way is fine, okay? So anyway, we need a formula or number which measures the degree of purity. So in decision tree, we have some options including entropy, information gain or information gain ratio, or a Gini index, okay, which can measure the degree of purity or impurity. So we're gonna talk about this later. So for example, these are the class value distributions. Here we have 100 no, no yes, and 50 yes, 50 no, and 25 yes, and 75 no, and 100 yes, and no, 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 no. Okay. So again, our goal here now is you're gonna define a function, okay, a formula, function or formula, which calculate the degree of impurity in these distributions, okay? So, for example, by the way, we're gonna compute the degree of impurity instead of degree of purity. Either way, it's fine. I say it's either way it is fine. But in this lecture, we're gonna use degree of impurity. Okay. Again, either way is fine. But we're gonna use degree of impurity or uncertainty. So we need a function or formula to compute the degree of impurity. Okay. So suppose we have that function, we have the formula or function which compute the degree of impurity of class values. Okay. Suppose we have that. Okay. Then in this case, the degree of impurity is very low, right? This is very clear actually. Everything is no. So this class distribution is very, very clear, very homogeneous, very pure, okay? So suppose we have a function or formula which compute the degree of impurity. Suppose we do, okay? then the output of function should be very low in this case, right? Because this case is very pure, very certain. So the degree of impurity should be very low, okay? So suppose you have function which measures, it computes degree of impurity. This value should be very low. Same thing here. Everything is y. There is no, okay? So if you have a function for degree of impurity, then that function returns very low value, small value for this case as well, right? So for these two, the function returns very small value, very low value. Here, we have 50 yes, 50 no. So if we have a function which computes the degree of impurity, actually that function should return very high value for this case. Why? Because in this case, it is very unclear, very impure. We have half yes, half no. This is a very unclear situation. Okay, so impurity or uncertainty is maximum. So if we have a function of degree of impurity, that function must return very high value for this case. Okay. Finally, for this case, if that function for degree of impurity, the output of that function should be somewhere between this and this. Okay, the output of this function for this case should be less than this and greater than this. Why? Because this is more impure than this, but this is more pure than this, right? So that's why if we have function, then the output should be less than this and greater than this. Okay.